If you've ever stepped on a running garden hose to stop the water, you already understand the physical logic powering modern computers and high-speed internet. That same squeezing action is exactly how a field effect transistor, or FET, operates. An FET is a microscopic component that functions as either a simple on-off switch or an amplifier for electronic signals. To see how it works, let's map the parts of our transistor onto that garden hose. First is the source, the intake point where current enters, like water from a faucet. Next is the drain, where current exits. Finally, the gate in the middle controls the flow. Applying pressure here restricts the channel's conductivity. This simple three-part mechanism allows us to govern the flow of electricity entirely without moving parts. It forms the mechanical foundation for all modern digital logic. Before FETs became the standard, engineers relied heavily on an older type of transistor called the BJT, or bipolar junction transistor. A BJT is current-controlled, meaning it relies on actual electron flow to toggle its state, which requires a constant drain of power. Returning to our hose analogy, a current-controlled device requires siphoning off a small amount of water to power the mechanical control valve that governs the main flow. A FET, however, is voltage-controlled. Instead of a secondary flow of water, the gate applies an invisible electric field to narrow the channel. Because this field acts at a distance, absolute zero current flows into the gate itself. Because the gate draws virtually no power to hold its state, your mobile devices can keep billions of these microscopic switches active and still run for days on a tiny battery. If you look closely at these devices, you'll find they generally fall into two main families. The first is the JFET, or junction field effect transistor. This is the classic, basic iteration of our garden hose model. The second, and far more common today, is the MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor. This is the upgraded standard required to run high-speed microprocessors. The major architectural difference between the two is insulation. In a MOSFET, the gate is perfectly insulated from the conductive channel by a microscopic layer of silicon dioxide glass. Because glass is an insulator, it prevents any stray electrical leakage between the gate and the channel. That absolute isolation allows engineers to pack billions of tiny MOSFETs directly next to each other on a single chip, without their signals bleeding together. Whether it's a JFET or a MOSFET, these components operate in three distinct regions. The first is cutoff. When maximum voltage is applied to the gate, the channel is pinched entirely shut. No current flows, which gives us a digital zero. The second state is the ohmic region. If we ease off the gate pressure slightly, a variable, measured trickle of current makes its way through. In this state, the FET acts as a variable resistor, allowing for precise analog control. Finally, we have saturation. By removing the restricting pressure entirely, the current flows at a maximum, steady rate. In a computer, this uninterrupted flow represents a digital 1. By shifting smoothly between cutoff, the ohmic region, and saturation, a single microscopic component can function as both a highly precise volume dial and a strict binary switch. To make sure a FET rests exactly in the state a circuit needs, engineers use a technique called biasing. Biasing is the practice of applying steady baseline voltages to set the default resting pressure of the gate. Depending on the design, you might see a fixed bias, a self-bias, or a voltage divider bias. These are just different physical arrangements of resistors used to dial in that exact resting voltage. This formula on screen is Shockley's equation. Engineers use this equation to predict exactly how much current will flow at a specific gate pressure. It gives us the precise drain current for a JFET based directly on the voltage applied to the gate. For MOSFETs, the math changes slightly to the enhancement MOSFET equation. The key difference here is the threshold voltage variable. Current will only begin to flow once the gate voltage surpasses this specific threshold limit. These mathematical models give engineers the exact blueprints they need to stack billions of microscopic parts together and guarantee they behave predictably every single time. When we put these properties to work, we get the infrastructure of modern electronics. In audio amplifiers, tiny fluctuations in the gate voltage are used to sculpt massive matching waves in the main current, driving large speakers with perfect fidelity. In your computer's processor, those same components act purely as switches, toggling between cutoff and saturation billions of times per second to execute binary logic. And they aren't limited to microscopic signals. High-power, heavy-duty FETs are explicitly designed to manage the massive energy loads flowing through electric vehicle charging stations and industrial solar power grids. Whether it's a whisper-quiet processor in a smartphone or the heavy current of a car charger, the exact same physical logic is at work. The field effect transistor is simply an efficient, voltage-controlled gate. By mastering the electric field, it acts as the invisible heart pumping data through the digital world. If this helped clear up how transistors actually work, please leave a like and subscribe to the channel. Let us know in the comments which electronic